Hi, and welcome back. This is video 3 of 3 for chapter 13, which deals with the subject of gravity. Now, in the first video, I gave you guys a rough overlay of some of the history of astronomy and introduced 3 laws that were empirical laws, Kepler's laws, to you. And in the second video, I introduced the law of universal gravitation, rather. And we did a number of examples with it, including examples that dealt with energy. Now, today, what I'd like to do is to go back and re-examine two of the three, rather, of Kepler's laws, and I'd like to try to derive them for you from the existence of gravity. Now, so if you remember what the laws were, we'll start just with Kepler's laws. The first one said, planets orbit the sun on ellipses with the sun at a focus. The second one said that a line drawn from the sun to a planet sweeps out equal areas in equal times. And the third one was an empirical law that said that the period of a planet's orbit squared is proportional to the length of the semi-major axis of the orbit cubed. So I'm not going to derive this one right here. And the reason why is because in order to understand the derivation, you need to have, at some point in your mathematical career, derive the equation of the ellipse. And that typically happens somewhere around calculus 3. And, that's sort of mathematics, unfortunately, beyond the scope of this course right now. What I am going to do, though, is to derive these two right here. Okay? So I'm going to start with the second one. So I want you to think of an orbit. We'll say it looks something like this. Let me put the sun somewhere over here. We'll say maybe here's the focus right there. And so here is a line drawn from the sun to a planet. Here's our planet right here. And we'll have the planet going around this way. All right. Now, when you say equal areas and equal times, what that means is that the change in the area over time is constant. Okay. So what I would like to do is to zoom in very close into this orbit and look at 2 points that are very, very, very close to each other, differentially close. Now, so I'm going to kind of exaggerate what they would look like here. Something like this. So maybe this is point 1 in your orbit, and point 2 in your orbit might be right here. All right. So to go from here to here, if things are kept sufficiently small, you're going to sweep out a very tiny angle. All right. So this is going to be a very tiny angle swept out. So this would be location 1 right here. This would be location 2 right here. And again, if you keep these things small enough, the distances from location 1 to location 2 are going to be more or less the same. They're going to be r. Now, to go from this r right here to this r right here in our travels, we go this way. Again, things are kept really small. Now, this right here would be dr, or if you think about this in terms of wedges of circles, the same thing basically is ds. Okay? Now, so we're looking at areas, right? And what you have here, if again you keep these things really close to each other, is basically two right triangles that are the same that are back to back. So here's our right triangles, okay? So the area of a triangle, or at least a right triangle, is 1/2 base times height. Okay. Now the base here would be 1/2 of r, or rather dr. Sorry. The height here is going to be r. Okay. Now, to be clear, this would be the height, and this is also r as well. But these things are so close together that this and this, these are more or less the same. So this is a very, very tiny separation, like I said. This is very exaggerated. So for one of these sides right here, the area would be 1/2 times the base times the height. Now here's the deal though. dr, like I said, is basically just ds, and ds is r d theta. Again, we're keeping r more or less constant because these are chosen very close to each other. So the area of one of these triangles would be 1/4 r squared d theta. The full area, which we'll call dA, is twice that. So in this particular calculation right here, dA is twice this. 2 times 1/4 is 1/2. 1/2 r squared d theta divided by dt. So this is Kepler's second law. Now you have a d theta dt. D theta dt, we know, is omega. That's your angular velocity of this thing as it goes around. So the change in area over time is 1/2 r squared d theta dt, or 1/2 r squared omega. Now check this out. I want you to think about now this planet at, I don't know, location 2, which as drawn is basically straight out. So the angle between its momentum at this point and r is 90 degrees. The angular momentum and magnitude, in this particular case, we'll say this planet has a mass of m, which we'll do it as a vector initially, r cross p, or we know from a magnitude standpoint, r times p times sine of the angle in between. But here, the angle is 90 degrees, r times p. Now, we also know from our discussion about angular momentum that you can write this as I times omega. Now, I, remember, is our moment of inertia. It's how far away something is from a point of rotation squared times the mass, mr squared. In this case is what I would be. So my angular momentum would be mr squared omega. And since there are no external forces acting on this thing, this is going to be constant. Now take a look at this, and take a look at this. They are, for all intents and purposes, the same. Okay? In fact, L over m is r squared omega. The mass is constant, 1/2 is just a number, and L is conserved. So as you can see, from a calculus standpoint, the reason why the second law is what it is entirely due to the fact that angular momentum is being conserved. So as I had said, what Kepler had discovered here was conservation of angular momentum. Okay. Now let's take a look at the third law. Now for the third law, I want to think about an orbit that is, for all intents and purposes, a circle. And you say, a circle? Hold on, I thought orbits were ellipses. Well, if you remember our conversation about circles and ellipses, circles are just special cases of ellipses. They are ellipses who have major axes and minor axes of the same length. Okay. So, again, here's our sun. Right here, stuck in the center. And here's our planet going around. Maybe there. The sun is going to have a mass. I'll call it m sub s. The planet has a mass. I'll call it m sub p. And it's going around like this. So what's making it go around? Well, obviously that's a force. That's the force due to gravity, which in magnitude, to be clear, this is just the magnitude, is the gravitational constant g times the mass of the sun times the mass of the planet over r squared. Now, this is a centripetal force. It's a central force. And we know that when you have central forces acting, for example, on planets, that you can write them as v squared over r. Now, the v here, remember, is your tangential velocity. V in this case is just r times omega. So you can write this again as m sub p r times omega squared. So here's what we have. G times the mass of the sun, mass of the planet, over r squared is equal to the mass of the planet, r omega squared. So the planet's mass cancels. All right. Now, so what I like to do is to write omega in such a way that exploits the fact that on a circle, this thing is experiencing uniform circular motion. Now, uniform circular motion means that the speed here is more or less constant. So this thing would sweep out 2 pi radians for every orbital period. Every time it goes around once, it sweeps out 2 pi radians. So I'm going to plug this into this. Now, what I'm going to do is to move these 2 periods over here to the left-hand side, and then move everything else here to the right-hand side. Now, when I do that, I have period squared on the left-hand side. On the right-hand side, I have 2 pi squared divided by g times the mass of the sun, and then I have the radius cubed on this side. Now, Kepler's third law says that the period of a planet's orbit squared is proportional to the length of that orbit's semi-major axis cubed. And in a circle, the semi-major axis is the radius. So what I see here is that the period squared is proportional to the length of the semi-major axis cubed. Okay? Now, we also have an actual expression for what that constant of proportionality is. So here, our constant of proportionality, which I'll call k, is 2 pi squared over g times the mass of the thing that's being orbited. And if you remember way back when, in my first video for this particular chapter, I mentioned that Kepler suspected that mass was in there somewhere, and he was trying to find an analytical fit to it, but he couldn't quite get it before he had died. Well, this is where the mass is. It sits in the denominator. Okay. So what we have here is, from the assumption of the existence of gravity and the calculus, okay, we have derived 2 of 3 of Kepler's laws, which were empirical laws. So this was a huge success. This is actually one of the big things that Isaac Newton was known for, was actually getting these laws from first principle. And by first principle, I mean from the existence of gravity. So there you go, the 3 laws. Now, that said, what I'd like to do is to play around just a little bit with the third one to show you, what you can do with it. Let me pull up something over here on my other screen. I had a reference here. Let's see. Here we go. So, I prefer, just because of how things are expressed, to not use this particular K when I'm dealing with the orbits of planets around the sun in particular, and that's because this K typically is expressed in MKS, and it's a huge number. Okay, it ends up being a little bit unwieldy to use. But if you remember, we had actually found, looking at the Earth's orbital data, K, by thinking about, the Earth taking 1 year and being 1 AU away. So in that particular arrangement, K was 1 year squared over AU cubed. And this is the K I'm going to work with. It's just convenient to the units that we deal with typically when we look at orbits. So what I'd like to do is to basically just play around a little bit with this to show you how you would use the third law. And in particular, I'd like to look, we'll say, at Jupiter. Now, if you look at the orbital data for Jupiter, Jupiter's semi-major axis is, let's see here. I see a distance from the sun, but I don't see, are these, let me verify this here. These are in kilometers. We don't want that. We want AU. All right, here we go. Here we go. This is better. Okay, so for example, we could ask the question, how long does it take for Venus to go around the sun once? What is the orbital period of Venus? Well, if you look at its orbital data, Venus has a semi-major axis that is 0.72. So here, t squared is equal to k times r cubed. And if we want to find what the orbital period is, we're just solving for t. So that means you take the square root of both sides. So here, t would be the square root of k times r cubed. Or 1 year squared over AU cubed times 0.72 AU cubed. And again, as you can see, the AUs are going to cancel each other out. And, you end up with years squared. You take the square root of it, and that gives you years, which is what you want. So if you were to actually do this, you get 0.611 years. Now, if you look up the sidereal period, that is how long it takes for Venus to take 1 full orbit around the sun, as seen from space. That's kind of what a sidereal means. It says it is 224.7 days. Well, again, this is in years. So if you convert this from years to days, just multiply it by 365. You get within reason, this is rounding, about 223 days. So not bad at all. Now, it's off here a little bit because we only have two significant digits in our semi-major axis. We know these semi-major axes to many, many more significant digits. So let's do another example. I don't know. Neptune. Now, Neptune takes 164.82 years to go around the sun once. I want to know what its semi-major axis of its orbit is. So again, t squared is equal to k times r cubed. We're given t, we're trying to find r. So r is going to be the cube root of t squared over k. Now again, yours cancel. You get an AU on the top. You cube that. Since it's cubed, that gives you one AU. So what do we have here? Well, if you actually do it, let's see here. 164.82 raised to the 2/3 power. I get 30.06 AU. And if you actually look at the semi-major axis length of Neptune is 30.06. So in this this particular law, we actually have a very powerful tool. All you need to do is to either figure out an object's shape of its orbit or its actual period it takes to go around something once, and you can deduce, the shape of the orbit from that. So the orbital shape gives you the time it takes to go around. The time it takes to go around gives you the orbital shape. Now, with this particular K, you can adjust this for any orbital system at all. If you remember, my conversation at the end of the first video I had done in this chapter, I mentioned that one of the things Galileo had seen was that Jupiter had moons that went around it, and all three of Kepler's laws worked perfectly fine there, with the exception of that constant of proportionality was different, and that was what had suggested again to Kepler that perhaps mass was important. So if you know the mass of the thing that's being orbited, you can find the K. Okay? And in doing so, now you have an accurate Kepler's third law, to handle the situation. Now, where would you use this? Well, I'll just briefly mention one place where you see this used in astronomy, and that's in planet hunting. Okay, so if you remember our conversation about centers of mass and rotation and stuff like that, one of the things that I said is that if you have a freely rotating object, it rotates about its center of mass. Well, one example of a freely rotating object would be a solar system. So, for example, in our own solar system, we have the sun sitting at the center, and then you have all these planets, and you have all this other debris and stuff, and it's all going around the sun. At least that's what we're told. But in truth, if you think of the solar system itself as one object that's rotating in space freely, it's rotating about a center of mass. And that center of mass actually doesn't sit inside the sun, it sits just a little bit on the outside. Now, so what that means is that if you look at how the planets go around the center of mass and how the sun goes around the center of mass too, because it's part of the object. Okay. You don't see this star fixed in place with things going around it. what you actually see is a star that, if observed over time, wobbles a little bit back and forth. And the period of that wobble has inside of it the periods of all the orbits of the planets that are going around it as well. So what we do when we planet hunt a lot of times is to observe a star and watch it move back and forth. It could be very complicated motion, but inside that complicated motion lies the periods of all the planets as they orbit. Now, we also know a tremendous amount about stars themselves. For example, given a particular classification of star, a particular type of star, we can tell you exactly what the mass is. So we have the mass, and what that means is that if we have the mass, we have K. And there's a modified version of Newton's third law that instead of having things go around the sun, has things go around the center of mass, that allows us to, knowing K and finding T, figure out how far away that planet is from the sun on average. That's basically what the semi-major axis is. So it allows us to actually look in, I guess you could say, construct the orbits of planets going around other stars based upon knowing the type of star it's going around and just looking at wobbles. Okay, so this is a good example of where you would apply, Kepler's third law. Okay, so next big subject I'd like to briefly talk about, we're not going to go too much into it, is just an explanation of tides. Now, so if you think about, we'll say the Earth and the Moon. Is the Moon going around the Earth? We know that the Moon goes around the Earth, just like the planets go around the Sun. Like we'll say it's going around like that. And, the Earth isn't this, sort of big stagnant body. There's water on the surface of the Earth. That water has mass. And, we know that, as per Newton's third law, if object A exerts a force on object B exerts the same force back on A, just in the opposite direction. So what that means is that as the Moon goes around the Earth, you have the water sitting on the Earth being pulled towards it. Okay. So what that does is to deplete water around here. And as the Moon goes around, it sort of tracks this water around. And, as the Earth rotates on its axis once every 24 hours, you have the same effect as well. Because as it rotates, that sort of big clump of water, if you want to think of it like that, is hanging out there. And, if you live here, for example, as the Earth rotates, you're going to see a peak of a tide, and then the tide is going to go down, and then you'd see a peak of a tide, and then a tide going down. Okay. Now, why do you see a peak over on this side? Well, the water's being pulled this way. So this is still, you could think of as a high tide. All right. Now, so you also have a similar effect due to the sun. The sun is going to pull, for example, on water over here. And so you have things called neap tides. You have all these complicated tides that occur. And the tides occur due to the fact that this side of the Earth is closer to the Moon than this side over here, so it's being pulled on harder. Now, tides don't just affect water, they can affect the interior of planets as well. A good example of which is the moon Io. Let me get a picture of it here. So this is one of the moons of Jupiter. And let's see here. Copy this. I'm going to paste it right here. So this is a picture of the surface of Io right here. And what you're looking at right here is a volcanic eruption. Now, the reason why this is relevant to our discussion about tides and stuff is because, Io itself is a very cold moon. It goes around Jupiter. Jupiter is really, really far away. The amount of radiant energy from the sun that falls on Io and on Jupiter is very small, which means that there's not enough energy from the sun to heat up Io. And as a consequence, because of its size, there really shouldn't be any sort of volcanic activity going on the inside until you factor in the fact that it orbits around Jupiter. Now, Jupiter is a concentration of a tremendous amount of mass. And so what happens is as this moon orbits Jupiter, one side of the moon is pulled more, harder than the other side. And what that does is to cause internal stress. And that internal stress manifests itself as heat. That heats up the interior, and as a consequence, creates volcanic activity. This is actually a sulfur volcano. It's one of it's the reason why Io has this sort of yellowish tinge to it. It's because of all the sulfur. So here, the gravitational tides, that's what they're called. That's what's really meant by tide. When we say tide, we don't really mean water. We mean the difference in gravity between one side and the other side of an object. So here, the gravitational tides have served to actually heat up the interior of Io, and as a consequence, make it possible to see volcanic activity. Io is one of the few other places that we know of in our solar system that experiences volcanic activity other than the Earth. Now, so that said, like I said, I don't want to get too far into a discussion about tides. I just want you to know that they're relevant, and this, is what's going on here. What I would like to talk about now is a different version of gravity. So I want to sort of step away from talking about Newton's version of gravity and talk about Einstein's version. So, one question you might have is why the need for another gravity? I mean, we have this one right here, This one works really well. Why the need to expand on it? Well, it has a lot to do with Mercury. You see, if you look at Mercury's orbit around the sun, when Mercury goes around the sun, not only does it orbit it, but it also has this sort of precession to it. A precession is a wobble to the orbit. So you can almost think of it sort of as sweeping out, kind of like lotus leaves, although it's not truly a good analogy as it goes around the sun. And the issue that you have here with that is that there's no justification as to why that would be the case under Newton's version of gravity. Now, so here's another way of thinking about this. And in order to understand it, we need to have a little bit of a discussion about something called relativity. Now, the stuff I'm talking about is in particular special relativity, which means that it only operates under certain explicit circumstances. Beyond those, you need to invoke a more generalized version of it called general relativity. And to understand this, we're gonna make two assumptions. The first assumption is this: the laws of physics look the same in all inertial reference frames. Now, so an inertial reference frame, remember, is one in which you are not being accelerated. If you remember the last video I did, we talked about centrifugal force and gravity and the Earth's rotation. Okay. Centrifugal force is not a real force, but if you're in an accelerated frame, you see this effect. So we're talking about a frame in which you are either at rest or you're traveling at a constant velocity. So you're not experiencing any acceleration. Now, the next assumption we're going to make is actually appears to be an observational fact. It appears as though no matter what frame you live in, as long as it's inertial, the speed of light is constant. It's also the same. Uh, we verified this experimentally. If you, for example, have a star coming towards you and you look at the speed of the light coming from that star, the speed that you see is not a combination of the speed of light plus the speed of the star. It's just the speed of light. If you have a star moving away from you very quickly that puts out light, you don't see a difference between the two. You just get the speed of light. Okay, so this is an experimental fact. Now we call these the postulates of relativity, or special relativity, rather. Now, so I want you. We're gonna play a thought experiment. So let's pretend that you have two people. You have one person, we'll say, standing here at rest. Um, they live in a frame or their coordinate system, is what I mean by frame. And I'm going to call it S. Typically, we call this the lab frame. And now I want you to imagine somebody over here that goes zinging by them and they're performing an experiment. Okay. Now they're moving at a constant speed, so the velocity is constant. Straight down the x axis. So their x axes and their y axes line up. I'm just going to differentiate between the two of them by putting a little dash on them, a prime. We usually call this the S prime frame or the moving frame. So the experiment that this person right here is conducting, and apparently they have, again, some sort of hip issue, is they have two mirrors that are directly across from each other, like this, and they're bouncing a beam of light between the two mirrors. Now, when their watches read 0, their y-axes line directly up. And if you were to ask this guy, what's the difference between, in length between these two mirrors, and you ask this person right here, how far are the mirrors apart, you're going to get the same answer. So the separation between these two mirrors, we're going to call capital L. Now, so when light hits a mirror, it bounces off. Okay, and it follows this law called the law of reflection. And the law of reflection says that the incoming angle and the exiting angle, we say the angle of incidence and the angle of reflection, they're the same. So for the person here who is at rest with this little experiment, but is moving by this person right here, if you were to ask them, hey man, what path do you see light take whenever it bounces between the mirrors? Well, he's going to say, duh, I see this. I see a mirror down here. I see a mirror right here. And I see light bouncing back and forth between it. Whoops. A distance of L. This is the path that it takes. Now, light travels at a constant speed. And that speed is the same according to this person and this person. And it's 3 times 10 to the 8th meters per second. So if you think way back to our simple 1D kinematics, we know that, V is equal to V naught plus A times T. And we also know delta x is equal to 1 half at squared plus v naught t. Now the thing is that if light is bouncing back and forth and isn't accelerating, remember it travels at a constant speed, then this is 0, which means that one way you can think about the distance between these two mirrors is that it is nothing more than the speed of light times how long it takes to go from here to here. So this is what the person in the prime frame sees, is light basically just bouncing back and forth between this mirror. A distance of L is how far it goes, and you can relate that distance to how fast light's traveling with time. However, what about this person right here? Now let's pretend that the person here in this moving frame is moving very, 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 very fast, a substantial percentage of the speed of light. So if you think about what this person right here sees, they see light leave that bottom mirror. Whoops, let me put this in arrow mode. They see light leave the bottom mirror and hit the top mirror. But in the amount of time it took for light to leave that bottom mirror and get to the top mirror, the person in the moving frame here has actually moved a substantial distance to the right. Now, the distance between the top and the bottom is the same. That's L. What's different, though, is the path that they see. Okay. Now, I'm going to call this path L prime. I'm going to call this path L, since it relates to S and this relates to S prime. Now, both of these people agree that the distance between the bottom and the top is the same. That would be L prime. Okay. What they disagree about is the path that light took. Now, you can actually prove this effect to yourself. So, have a friend take and just standing still, they throw a ball straight up into the air and they catch it. If they're standing still relative to you, you'll both agree that the ball went straight up, hit its peak, turned around, and came back down. Now, if you have that same person walk by you at a constant pace and they throw the ball straight up and let it fall straight down, it, according to them, is going to go straight up and fall straight back down. But what you see is a combination of the ball going up and down and their walking path, the speed that they're walking at. So they see straight up and down. You see a parabola. So you both agree on the height, but you disagree about the path. And that's exactly the same thing that's going on here. Now, the law of reflection says that this bounce here is not an arc, but a sharp cut, which means that what we have here is a right triangle. Okay? The sides of this triangle are L prime, which is the distance between the mirrors, and also the path that the person who's moving says that light takes. We have D, which is the speed that the person is traveling at times how long it took them to get from here to here, which is incidentally the same amount of time it takes for the light to get from here to here. And then you have L, which is the path that light took according to the person who is in the lab frame, which would be, since it's the speed of light, c times t. C times t and v times t. Oh, now there's something going on here. This is a problem. This is a big problem because look, this is a right triangle. And my understanding about right triangles is that the hypotenuse is always longer than any of the sides. But this side here and this side here, according to the math, had the same length. This doesn't make sense. Now, what do we know? We know that the speed of light experimentally is the same. They both measure 3 times 10 to the 8th meters per second. They both agree about how quickly light travels. What they disagree about is the path. And since light isn't being accelerated, since this is an inertial frame, then the only thing that could change, other than the path, which they disagree about, is time. So, what you have here is one of the underlying tenements of classical physics, the stuff that we've been doing, being shattered. The person in the moving frame is going to experience time differently than the person in the lab frame. And you can actually find a relationship between the two just using the Pythagorean theorem. So here we know that the sum of the square of the sides is equal to the square of the hypotenuse. So Vt squared plus Ct prime squared is equal to C times T squared. So we can find a relationship between the times. I'm going to move this over here, over to, actually I move this over to the right-hand side. Now I'm going to pull the T squareds out. And now I'm going to divide both sides by C squared. I'm going to take the square root of both sides and move this over here under that. One over the square root of 1 minus v squared over c squared is defined to be something called gamma, which is used in relativity all over the place. So so there you go. That's the relationship between the times. Now, importantly, what this means is the times aren't the same. And if the times aren't the same, one question you might have is what other effects does having a speed of light that's constant, what other effects does this mean? Or does this cause, rather? And one of the things it causes is a relationship between energy and mass. Now, I'm not going to derive this. If you're genuinely interested in learning about special relativity and some of the consequences of this stuff, take a class called Modern Physics. It's typically taught after university physics too. Now, so what this means here is that when you have two frames like this that are different, you can't rely upon time being the same. So now you think of time more as a coordinate. Okay. So we have these things called events. Now, a good example of event is a party. So if you throw a party like a birthday party, doesn't that happen at a location and at a time? Well, sure. Meet me at Joe's bar. Here's the address. There's your location, your position in space at 8 o'clock. So events have positions and have times. All right. And so your position, you have an X position, a Y position, and a Z position. And now we also have a position in time as well. So we have 4 coordinates when it comes to actually locating something now because of the fact that you can't rely upon time being the same everywhere in the universe, which means that you have 4 dimensions. And if you take space and you add it to time, you have space-time. So 4-dimensional space-time is a consequence of the fact that time isn't the same everywhere in the universe. Now, I'd like to remind you of something that I'd said last video, and that's that because gravity, or the force due to gravity, goes like 1 over the distance squared, there's no place in the universe in which you can get away from it. So, one way you could think about the universe, or locating something in position, we'll say, is that it has a position in space and in time, and there's also an associated gravity there. Now, this is what precipitated the development of something called general relativity. General relativity is Einstein's answer to gravity. And to understand it, what I'd like to do is to sort of give you a little bit of insight into a different way of thinking about forces. Now, what you're looking at here is not a toilet, although it does look a lot like a toilet. If you've ever been to a mall or some other business here, um, where they have a one of these doohickeys right here. Basically, what happens is you put a coin in here, the coin hits this, and it sort of makes its way down the funnel like that, riding along the curvature down to the bottom. I call these things coin suckers. Now, so what makes this thing go around in circles? We know is the normal force and gravity. So what happens is as this thing goes around in the circle, your coin is sort of riding around at an angle like this. You have the force due to gravity pulling it down. That's a very bad down direction, but that's what that is. And then because you have this physical boundary, this physical funnel boundary, you have a normal force that's pushing inwards. And this normal force really is your centripetal force that keeps this thing along its path. Now, as these things go down, you'll hear a noise. You'll hear like so coin rolling in there. And since you hear a noise, what you have is energy being lost. You have frictional forces at work, and what that does is to take some of the motion energy away, and so what that it causes to drop lower in the curvature. And as energy is robbed, it goes lower in the curvature, and then lower in the curvature as friction takes some motion away, and then eventually it finds its way down where some guy just got a quarter from you because you wanted to watch it go around in a circle. Now, there's another way of thinking about this. Instead of it being normal forces and gravity, what's happened here is the coin is caught in the curvature of the funnel. That makes this a geometry thing. It's just a geometry trick. But what it requires is an understanding of curvature. Now, another example of this is a trampoline. If you think about a trampoline as sort of having a flat surface like this. Now, what I'm going to do is to grid it just a little bit. So we're going to grid it. I'm sure there's easier ways to do this, but this is kind of cathartic right now. And then we'll grid it this way. Whoops. I guess I made it a little too long. That's okay. So here's the surface of a trampoline, and all I've done is to put a grid on it. You could conceivably do the same thing to a trampoline that you had, access to just with chalk. Now, if I were to take and put a bowling ball in the center. So here's a bowling ball right here. the weight of that bowling ball is going to cause this trampoline to sag. And if you were to look at it on edge, you would see a sag that looks like that, with a bowling ball sitting at the bottom. So if you were to look at these grid lines would actually be bent inwards like this towards the bowling ball. Now, if you took a tennis ball and you rolled it this way, as this tennis ball rolls on the flat surface of the trampoline, it's all good. But when it hits the curvature, its path is going to be bent and it's going to track along the curvature. So what you've done is you've altered the path of this tennis ball by changing the curvature of the thing that it's sitting on. We haven't talked about any real forces. All we've done is just to change the path by altering the curvature. Now, imagine instead of this being a bowling ball with a tennis ball, imagine this being a star. And this surface right here that it's sitting on is actually space-time that it's sitting in. If you pretend that mass bends space-time like a trampoline, then you can imagine a planet going around the sun because it's trapped in curvature and not because there's a force between it and the sun or that star causing this motion to occur. So we've taken a force and we've turned it into a geometry game. Now, I want to be clear. This does not make the math easier. In fact, it increases the difficulty of the math by several orders of magnitude. But it turns out that if you do that, you're able to explain the orbit of Mercury around the sun. You get it correctly. And this is generally the way we think about now gravity. We think about gravity as though it's an effect due to the curvature of space-time. Now, how does that curvature get there? Well, mass causes it. But if you remember way back here, I said one of the consequences of this discussion about special relativity is that mass is also equivalent to energy. So the presence of energy can cause space-time to be bent as well. Now, one interesting consequence of this is that light, too, can be caught in bent space-time and have its path altered as it goes through space. That's not something that's predictable as per Newton's version of gravity. Newton's version of gravity depends upon the thing that's being affected by a mass to have mass. But it turns out light itself, as a particle, doesn't have mass. It has energy but no mass, which is something that we'll be discussing when we talk about it in university physics too. So what you have here is the potential to have light's path bent by the presence of mass or energy. Now, back when Einstein came up with this theory, he actually did a calculation to determine how much of a bend that you would see. And during an eclipse of the sun, what they did was to look around the sides of the sun to see if they could see vestiges of light from behind being bent around. And they did. Now, we actually see this happen in nature quite a bit, specifically in astronomy and around galaxies. Here's an example of one right here. Let me copy this real quick. This is an example of the gravitational lens. So you have a galaxy, which is a tremendous concentration of mass, bending light around it. And the light is actually a galaxy that's sitting behind it. So you're seeing light that's bent around it. And as a consequence, has produced a halo of that light. This is gravitational lensing. This is not possible without this being true. So even though Isaac Newton's version of gravity served us very well, a more correct version of gravity would be Einstein's version of gravity. Now, we don't use Einstein's version of gravity everywhere, though. I'd say for terrestrial use, and maybe 8 times out of 10, using Newton's version here, this is fine. Okay, you don't want to whip out the big gun, basically, until you absolutely need it. Okay, and part of that has to do with the fact that the math is incredibly complicated. Now, that said, there are terrestrial uses for this, or semi-terrestrial, I say, and a good example of which are GPS satellites. When we first put GPS satellites up into orbit, one of the things we had issues with was the fact that they were, even though they had atomic clocks on them keeping time, the time would drift very quickly away from what was being measured on the ground. Now, that has everything to do with what we had done up over here, with time being different on the satellite as opposed to being on the ground. Now, somebody pointed this out. They actually wrote some software updates to include the fact that as the satellites went around the Earth, they were trapped in the gravitational well of the Earth, the space-time bend. And when they took that into account, suddenly the satellites were keeping correct time and didn't drift. So this is a very real effect. Okay. Now, one example that you see this sort of evoked in is something that most people have heard of, and these things are called black holes. Now, all a black hole is mass that's been packed in to such a small volume that it's bent space-time so badly that there's a point in which light can't get away. So if you think about the curvature of space-time being a measure of how fast you need to be going in order to escape, gentle curvature like this offers you a good opportunity to escape. But if you think of this sort of as being a cliff, there is a point, we'll say right here, to where you would have to be traveling at the speed of light or greater in order to get away. Now, pop sci, for whatever reason, likes to think of black holes as being punctures through space-time somehow. And as a consequence, you have these things that they kind of came up with called wormholes, where you punch through one side and you exit the other side, and you can throw something in and it comes out. Light years upon light years away. Like I don't know, Stargate or something like that. Now, this doesn't seem to be realistic right now. What's meant by the term hole in this particular case is a mathematical thing. Black holes were predicted to exist before we found them. They were a consequence of Einstein's general theory of relativity, and there is a divide by zero in the equation. And where you have these infinities pop up because you're dividing by zeros, we call these holes in equations. So, as a consequence, they really aren't a puncture in space-time. They're a place in a mathematical equation where things sort of blow up. All right. Now, again, remember, math is used to model nature. It doesn't dictate how nature works. Now, another name that you see used with respect to black holes are singularities. Again, a divide by zero thing is a singularity in a mathematical equation. Now, the black part comes from the fact that if light can't get away, if the speed to get away here is greater than that of light, well, you can't see it. It's black. Light can't get away. So what you do instead see are very weird visual effects. So if you were to see a black hole directly, you might see something that looks a little bit like this. So this is a simulation of the gravitational lensing effect that you have as this black hole passed basically across our line of sight of the Milky Way. The Milky Way is the band of stars that you see across the sky in a dark area. That's actually our galaxy. So you see these visual effects that happen around it, but this isn't the black hole. This is the black hole right here, and you can't see anything here. This is black. Okay. But you see these bending effects because you have such an extreme curvature of space-time. Things are bent so much that light is just, being slung around it out like that. Now, light that does fall into it simply just adds to the mass of the black hole. All right. Now, that said, if you remember way back when in the previous video, I had talked about, you know, conservation of energy and gravitational potential. So you can actually think of, or you can find rather, the point of no return for something that has mass using just Newton's version of gravity. So if you remember, the total energy looks like kinetic energy and potential energy. M1 I'll call the black hole. M is just something, whatever it is being attracted to it. Now it's bound if this is equal to 0, and what we're looking for is the place where light would be bound. Now light always travels at the same speed. Like I said, it's the speed of c. So you would have 1/2 mc squared minus g m1 m over r is equal to 0. And these masses right here cancel. This would be the mass of your black hole right here. So the radius of your black hole, that is the point. And I say radius of the black hole, it's not true. That's just the point or the distance away from the black hole in which you're basically out of luck. You can very easily solve for it just by solving for r. So it ends up being 2g times the mass of the black hole divided by c squared. And this is called the Schwarzschild radius. Or the event horizon would be that point right there. Why do we call it the event horizon? Well, if you were to go out to the ocean and look at it, you have the sky above, and then you have the water below, and the horizon marks the point at which you can't see the sky anymore. So if you try to look below the horizon, you can't see anything. You don't see the sky. So here, this is a horizon in that if you try to look below it, you cannot see events occur. And that's because in order to see something, you have to see light coming from that. And light can't escape beyond this point. Okay, so that's it for this discussion about gravity, and I will see you again.